Sorry, guys, that I had to stop right in the middle of that, but I had a phone call that I had to take, so I apologize for that. My husband called. So anyway, you can just, uh, I'm sure, hopefully you haven't listened to that whole to the end of that video. I mean, it wasn't very long, but still. Okay, so let's look at what we were doing. We had already, um, we were asked to find delta TF, so we used the equation for delta TF, and that is KF times M, and M is molality. Well, molality is moles over kilograms, so they gave us 17.5 grams of sodium chloride, so we had to convert that to moles. So 17.5 grams of sodium chloride is 0.249145 moles. And so then we put that in our molality equation, and then we have to divide that by kilograms of solvent. They told us we had 933 milliliters of solvent, which is water. Water is the universal solvent. And so we had to convert that to kilograms by dividing by 1,000. Because again, there's 1,000 grams in 1 kilogram. And again, 933 milliliters is the same as 933 grams of water, because 1 gram of water is 1 milliliter. And so that gives us 0.933 kilograms of solvent. So then we divide our 0.299145 moles of sodium chloride by 0.933 kilograms of water. And we had just gotten, I think we had just done that. And we got 0.320. But I'm going to check that again just to make sure, because it's been just a minute since we did that. So 0.299145 divided by 0.933. And yes, that gives us 0.320627, so on and so forth. And again, we're not rounding yet because this is not our final answer, but we are going to substitute that amount in for molality in our delta TF equation. We do still need KF. So if we look at our information here, I don't have KF, but I do have it over here on this one. KF is negative 1.86, and again, that is for water. So I'm going to go ahead and put that on here too so I don't forget it. KF is equal to negative 1.86, and that's for water. And I'm sure it has some units as well, and we'll get to that later. So let's go ahead and, so now that we have that KF is negative 1.86, we can substitute that into our delta TF equation. So KF, negative 1.86, times our M, which is our, let me go back to that, 0.320, and I'm going to write like 6 numbers down, 627. Again, I'm not rounding anything yet. So we've got our negative, we got our 0.320627, and then we're going to multiply that times our negative 1. I was thinking maybe I could go back. Yeah, okay. So negative 1.86. And that gives us, and now this is our final answer. So we're going to round to the correct number of significant digits. In our problem, there are 3 significant digits in 17.5 and 3 significant digits in 933. So then we're going to round this to 3 significant digits. So it would be negative 0.596 would be our 3 significant digits, and the 3 does not change that 6. So it's negative 0.596. And again, this is going to be degrees Celsius. I think that KF, negative 1.86, has, I think it's like Celsius over moles or something like that, or molality or something like that. So anyway, our unit is degrees Celsius. Okay, so let's check the answers then and see if that's what we got on the answer sheet here. Yes, negative 0.596. All right, great. Okay, let's keep going then to our next question. If 125 milliliters of a copper 2 chloride solution reacts with enough aluminum to produce 0.550 grams of copper by single replacement, What was the molarity of the initial copper 2 chloride solution if aluminum chloride is the other product? Okay, this is a problem that you guys had on another test and everybody struggled with it. So let's go ahead and just write down what we have right now. So we have 125 milliliters of copper 2 chloride. So 100, and again, I'm just writing this on my iPad. And copper 2 chloride, again, copper 2 means copper with a positive 2 charge. Chloride is chlorine with a negative 1 charge. So if copper is positive 2 and chlorine is negative 1, then our formula is CuCl2. We're going to be needing that in a minute. Anyway, so we might as well go ahead and write it. All right, it's going to react with aluminum to produce 0.550 grams of Cu. So we're going to have 0.550 grams of Cu. All right? And we want to know what was the molarity of the initial copper 2 chloride. So molarity of the copper 2 chloride solution is what we want to know. If the initial copper 2 chloride solution, if aluminum chloride is the other product. So then, obviously, guys, I hope you can tell here that we're going to need a balanced equation, okay? We're going to be reacting CuCl2, which is copper 2 chloride. It says it reacts with enough aluminum. So it's going to react with aluminum, and it's going to be single replacement, and we're going to get aluminum chloride. And we're also going to get Cu. It tells us here it's going to produce Cu. And it's going, if the other product is aluminum chloride. So again, aluminum is +3, chlorine is -1. So if aluminum is +3 and chlorine is -1, then the formula for aluminum chloride is AlCl3. Again, it's important to make sure that we have our reactants and products correct. So copper 2 chloride, copper 2 is +2, chloride is -1, so that's CuCl2. Aluminum chloride, Al is +3, chloride is -1, so it's AlCl3. So when you're writing these, you have to make sure you write the correct formula of the reactants and the products. Also, this is the element copper, and copper is not part of Brinkelhoff, so it is just Cu. We would not have to put Cu2. Okay, so now I hope you realize we need to balance this equation before we do anything. So again, we have 1 Cu on both sides. We have 1 Al on both sides, but there's 2 chlorides on the left, and there's 3 on the right. So the least common denominator there is 6. So we're going to put a 3 here in front of the Cu, and that will give us 6 chlorines. And if we put a 2 in front of the AlCl3, that gives us 6 chlorines. So now we're going to have to work on our aluminums. It looks like we're going to need 2 aluminums on both sides. So put a 2 in front of the Al, and we're going to need 3 chlorines, coppers on both sides. Put a 3 in front of the Cu. So that gives us 3 coppers, 6 chlorines, and 2 aluminums on each side of the equation. All right, so now that we have a balanced equation, now we can actually figure out our problem. Okay, we want to know the molarity. Well, how do we find molarity? If we go back and look at molarity, well, here's our formula. Molarity equals moles over liters. Okay, so molarity is equal to moles over liters. So we want to know the molarity of the copper 2 chloride. And again, I just wrote that down. Molarity is moles over liters. And we need the molarity of the copper 2 chloride. So that's going to mean I need moles of copper 2 chloride over liters. Well, I know I had 125 milliliters of copper 2 chloride. So how do I convert that to liters? Well, I divide by 1,000. Or just move your decimal 3 places to the left, and that gives you 0.125 liters. So there's my liters. Okay? And again, we're doing copper, we need molarity of copper 2 chloride, so I have liters of copper 2 chloride by moving my decimal 3 places to the left, 0.125 liters. But now I need moles of copper 2 chloride. Well, could I use this balanced equation to get moles of copper 2 chloride? And notice they gave me 0.550 grams of copper. So could I take 0.550 grams of copper and convert that to moles of copper 2 chloride? You bet I can, because we've already done that once today. We did a mass mole problem. Well, this is another mass mole problem. So we're going to take our grams of copper that we produced in this reaction, and we're going to put it over 1. And then we're going to change those grams of copper to moles of copper 2 chloride using this balanced equation. Again, before we can do that, we know that we're going to have to change grams to moles of copper. So we're going to have to put grams of copper on the bottom so that it will cancel out, and we're going to change to moles of copper. And then, of course, we know we're going to have to use the balanced equation to do this. So 1 mole of copper is going to be the number of grams of copper on the periodic table, which I think, and if this is not correct, don't hold it against me. But again, I'm just doing this for memory because I'm not taking the time to look it up. But you guys need to take the time to look it up on the test, okay? So I'm thinking it's 63.5. Remember, we want one place past the decimal. So I think there's 63.5 grams of copper in 1 mole of copper. So my grams of copper cancel out, and I have moles of copper, but that's not what I need. Remember, we're doing the molarity of copper 2 chloride. So I need moles of copper 2 chloride here. So I've got one more step to do, and that's going to be a mole-mole ratio for my balanced equation. I'm going to put moles of Cu on the bottom so it will cancel out. And I'm going to put moles of CuCl2 on the top so it will cancel out. So then get my coefficients for my balanced equation. In front of CuCl2, I have a 3. And in front of Cu, I have a 3. So it's 3 moles of copper to 3 moles of copper 2 chloride. Again, 3 to 3 is the same as 1 to 1, so if you want to go ahead and reduce that to 1 to 1, that will make it a little bit easier. So now we can see on the top, if we reduce this to a 1 to 1 ratio, on the top we have 0.550 times 1 times 1, and on the bottom we have 1 times 63.5 times 1. So it looks like we have 0.550 on the top divided by 63.5 on the bottom. So let's go ahead and multiply or divide that out. So I'm going to clear my calculator. And on the top, we said we have 0.550, and on the bottom, we have 63.5. And that gives us 0.00, and again, I'm going to write 6 or 8 numbers, 0.008660142, because that 7 makes that last one 2. Okay, and again, this is moles of copper 2 chloride. CuCl2. Again, that's my unit now. So, again, you guys, that is what I needed right here. I needed moles of copper 2 chloride. Well, now I have it. So now all I got to do is substitute it in up here, 0.008660142 moles, and then divide it out. So I've already got that number here, 0.008660142 moles, and I'm going to divide that by that 0.125 liters there, divided by 0.125. Okay, and then this gives me the molarity of that initial copper 2 chloride solution. Again, all of my measurements in this problem have 3 significant digits, so I need to round this to 3 significant digits. My first 3 significant digits are the 692, and this 9 after the 2 makes the 2 a 3, so 0.0693. So my answer here is 0.069. And that is molar. So 0.0693, and I'm going to write it down here. 0.0693 molar copper 2 chloride. Okay? And now let's go back. To our answers and see if that's what we got on these answers. So right here, 0.0693 molar, or 693 molar. So awesome sauce. All right, going on down now. We now have an equation, and we want to write our complete ionic and net ionic equation. And again, we're using these rules, and you guys, I noticed on our test over acids and bases that we had some trouble with this. Again, dissociate means to break apart, and they will only break apart if it is a strong acid, a strong base, and a salt. Okay, water does not break apart, precipitates do not break apart, and weak acids and weak bases do not break apart. So how do I know what's a strong acid and a strong base versus a weak acid and a weak base? That's where you use these rules, guys. Okay, this rule tells us that salts break apart. Well, we know at the end of this equation we're going to have a salt whenever we do this double replacement neutralization reaction. So that salt is going to break apart unless it is not soluble. So in order to figure out if it is soluble or not, we have to use this solubility table that we have here, and I will make sure that you have that for the test. Okay? The next thing is acids are weak except for these 6. So if it is HCl, HBr, HI, HNO3, HClO4, or H2SO4, you better break it apart. If it's not one of those 6, do not break the acid apart. Again, remember, acids start with hydrogen. So if it starts with hydrogen and it's one of these 6, break it apart. If it doesn't, then don't break it apart. Bases are weak, okay? All bases are weak except for hydroxides, that's OHs, that are with a group 1 or 2 metal. So LiOH, NaOH, CSOH, KOH. Okay, those are group 1 metals. Those are going to be strong bases. CaOH2, BaOH2, SrOH2, any of those group 2 metals like Ca, or not Br, Ba, Sr, those are group 2 metals with a OH. Those are strong bases and they need to be broke apart. But if it's not one of these 6 acids, if it's not one of those OHs with a group 1 or 2 metal, use your periodic table and see what those are. Then do not break it apart, okay? So we got to be careful about that. So let's go ahead and do this then. So this is number 6. We have HCl plus CaOH2. And again, this is double replacement. So the H goes with OH and we get water. And the salt is going to be the Ca and the Cl going together. Again, the H and the Ca are switching places, so the Ca is going to go with the Cl. Again, you have to write a correct formula. So Ca is +2, Cl is -1, so the correct formula is CaCl2. Okay, so you guys, this is HCl. Let's see, is it a strong acid? You bet it is. So I'm going to write up there, strong acid. It will break apart. What does it break apart into? Well, hydrogen is +1. Chlorine is -1, so Cl-. Okay, going on. CaOH2, that's our base because it has OH in it. Remember, Arrhenius bases have OH. Is it a strong base? Well, how do I know? Well, if that metal is a group 1 or 2 metal, it is a strong base and it breaks apart. If that is not a group 1 or 2 metal, then you do not break it apart. It's a weak base. So let's see, is Ca a group 1 or 2 metal? Yes, look on your periodic table. Ca is a group 2 metal. So therefore, this is going to break apart. This is a strong base and it's going to break apart. So let's break it apart. Ca is +2. And you guys, there are 2 OHs here. So we put 2 OH with a -1 charge. Okay? Because there's 2 OHs there. Again, I'm going to put parentheses around that so it doesn't look like 20. It's 2 OHs. Okay. Does water break apart? Well, let's look at this. Let's look at this rule. All other metals are non-electrolytes. That includes water. Or all other materials are non-electrolytes. That includes water. Water is a liquid. It's a non-electrolyte, so it does not break apart. So it's just H2O. Okay, CaCl2. Well, you guys remember that's our salt. All salts are strong electrolytes unless it's insoluble. If it's a precipitate, it's not. So let's see, is CaCl2 soluble or not? So let's look. Cl soluble except Ag, Hg, and Pb. So this is not AgCl, HgCl, or PbCl. This is CaCl, so that means it's soluble. All Cls are soluble except for those 3. This is not one of those 3, so it is soluble, so this means it breaks apart. It is a soluble salt, and it will break apart. So let's break it apart. Ca is +2, and then you guys, there are 2 Cl minuses there. Cl2 means 2 Cls with a -1 charge, because we know Cl is -1. All right? So there is our complete ionic equation. Now we have to do our net ionic equation. How to do the net? You mark out things that you have that are the same on both sides. So do we have an H on both sides? No, we don't. Do we have a Cl minus on both sides? Yes, we do. And you guys, something I forgot to do here, we need to go back and do real quick before we finish this up. You guys, we have to balance this equation, and I did not do that. I apologize. There are 2 H's here and 2 Cl's here, so we need to put a 2 here in front of the HCl, and it will be balanced, okay? Yeah, because this 2 H's here and 2 OH's here gives us 2 waters, so we also need to put a 2 in front of this. So what we have then is we have 4 H's, 4 H's, we have 2 Cl's, 2 Cl's, we have 1 Ca, 1 Ca, and then we have 2 O's and 2 O's. So now we're balanced. So we have to put a 2 in front of the H, we have to put a 2 in front of the Cl, and we also need a 2 in front of the water here to have it completely balanced. So now, this is our final balanced complete ionic equation. Now we need to do the net ionic equation by canceling out the things that are the same on both sides of that arrow. So you see we have 2 H pluses here, but we don't have 2 H pluses over here, so we can't cancel those out. We have 2 Cl minuses here, we have 2 Cl CO minuses here, so we can cancel those out. We have one Ca2 plus here, one Ca2 plus here, so those will cancel out. Okay? Two OH minuses here, but we don't have two OH minuses over here. So after we cancel everything that's the same on both sides of the arrow, what we have left is 2H plus 2 OH minuses gives us 2H2O. Well, what else can we cancel out? We can cancel out all those 2's. All those 2's will divide away. They will reduce is what we're doing there. So what we have left after we reduce it is we have H plus OH minus yields H2O. Now you guys, this will be the final net ionic equation if you have a strong acid and a strong base and your salt is soluble. Now on our test from last week, we had a strong acid and a strong base, but the salt that we got here, it was BaSO4. Okay, BaSO4 is not soluble. SO4 is soluble except for Ba. So BaSO4 was not soluble. So that salt over here was BaSO4. It was a precipitate, which means it will not ionize. It will not break apart. So it had to stay whole. It had to stay as BaSO4, okay? So that's the reason why, even though we had a strong acid and a strong base, we did not get this as our final net ionic equation because the BaSO4 was not soluble. This CaCl2 is soluble. So if your salt is soluble, if you have a strong acid, a strong base, and your salt is soluble, this will be your final net ionic equation. All right, let's see if we did that correctly. Yes, we did. Okay, so moving on. Looking at our, now we're going to do hydronium ion concentration, and we're going to do pH. Remember that to find the pH, you have to do the negative log of this hydronium ion concentration. So all we got to do here is negative log of 1 times 10 to the minus 10. So and I really like using my scientific calculator for this because it's easy to type in. So I just do negative log 1 times 10 to the minus 10. Make sure that looks right. Yes, close my parentheses and equals. And I get 10. So the answer to this one is 10. If we look on our, there you go, it is 10. Okay, moving on. Now we're given a pH and we need to find the hydronium ion concentration. Okay, what you're going to do there is just the opposite. You're going to do 10 to the negative pH. So 10 to the negative 4.31. So clear and then do 10 to the negative 4.31. And we get this. If we want to write it in scientific notation, it is going to be 4. Okay, this 7 makes this 9 a 10, so this goes up to 4.90. So we're going to get 4.90. And what number are we doing here, by the way? We are doing number 8. So number 8, we're going to get 4.90 times. And then we've got to finish putting this in scientific notation. So we're going to move that decimal till we get a number between 1 and 10, which will be the 4.89. So move it 1, 2, 3, 4, 5. Since we made the number bigger, we went from this 0.00000489 to 4.89. We have to make our exponent negative. So that since we moved our decimal 1, 2, 3, 4, 5 places, it's going to be times 10 to the negative 5. Okay? And then that's going to be molar because this is a hydronium ion concentration. Again, you can't just write 10 to the negative 4.31. You have to punch that in the calculator, okay, to get that concentration. Okay, moving on. This is something that we also had trouble with last week on our exam, was completing this equation, or I'm sorry, completing this data table. All right, what we're going to need to do is basically on this, we're adding and subtracting. And when it comes to significant digits, when you're adding and subtracting, you do the least number of places past the decimal. So basically, I've got to look at the places past the decimal in this table and make sure that my places past the decimal are the same in the row all the way across. So in this row, I have 25.0, 25.0. Well, that needs to have 1 place past the decimal. This row will need to have 2 places past the decimal because there are 2 places past the decimal in these measurements in this row. This row will need to have 2 places past the decimal. This row, well, this one's going to stay the same. But anyway, so the other problem some of us had was finding the volume of titrant used. Well, again, the titrant is the NaOH that's in our burette. To get the volume of titrant that you used, you have to do the final minus the initial burette reading, okay? So just to reiterate that, to get the volume of titrant, or which is NaOH, that you used, you have to do the final minus the initial burette reading. And it was a very simple calculation that many of you missed. I told you that in the video when we went over how to do the calculations in the video. So then that makes me think either you didn't watch the video or you didn't pay attention. So please, make yourself a note of that. If you're not sitting here right now doing the problems as I go over this video, then make yourself a note to find that so that you won't miss this on the final. Because, guys, this final is going to count 20% of your grade, and you're not going to get to redo it. So you have to do it right the first time. So we're going to do the final minus the initial burette reading to get the volume of NaOH that we used. So the final is 30.25, and I'm doing this on my calculator here where you guys can see it, 30.25 minus, and then our initial reading here was 4.75. So we're doing minus 4.75. And when we do that, we get 25.5. So that's what I'm going to fill in my table here, 25.5, and I'm going to write it in there so that I'll have it. All right. We're going to do the same thing for this one, 28.22. And then our initial was 2.60. So minus 2.60. And that gives me 25.62. The other thing I didn't count off here, but you really should have done, is you should have put the unit in there. Because if you will notice, everything that I do here, it already has units. So I need to put the units. All right. So now we're going to do averages. You guys know how to do averages. Add the two together and divide by 2. So just add the 2 together and divide by 2. That is simple. So 25 plus 25 divided by 2 is going to be 25.0. And that is going to be 25.0 and then milliliters. Again, have to have 1 place past the decimal because all the measurements in that row have 1 place past the decimal. This one, 4.75 plus 2.60. So 4.75 plus 2.60 equals, and then I got to divide it by 2 to get the average. So that's 3.675. Well, 3.675, I only need 1 or 2 places past the decimal, so 3.675, I'm going to round up to 3.68. Okay? Same thing with this one, 30.25 plus 28.22. 30.25 plus 28.22. So 30.25 plus 28. Oh, wait a minute, I forgot to clear. 30, don't forget to clear. 30.25 plus 28.22. And let me look again and make sure that's right. 30.25, my memory's not very long sometimes. So equals, and then divided by 2 equals. And I get 29.235. Again, I'm going to need 2 places past the decimal, so 29.24 is what I'm going to put here. 29.24 milliliters. All right, moving on, 25.5 and 25.62. So, and you guys, that actually should have 25.50 there. Mess that up. So 25.5 plus 25.62. So 25.50 plus 25.62. Oh, I forgot to close it out again. So 25.5 plus 25.62 equals, divided by 2 equals. Okay, 25.56. So 25.56 0.56 milliliters. Okay. Last one. This one is the same across the board, so 0.750 molar. All right. So now, that's all you have to do to fill in that table and to get your points for filling in that table. Not miss anything. All right. So now we got to do the experimental acid molarity concentration. To get that, guys, we're going to use our equation. MA VA equals MB VB. Again, the A's are for acid, the B's are for base. All right, so our acid is our HCl. So you guys, this is our volume of acid that we used. So that is VA, volume of acid that we used. Well, MA is what we're looking for. We're looking for the experimental acid molarity. Well, the MA, that's acid molarity. So we're looking for MA. MB, right here, molarity of titrant, NaOH. That's our MB. Because NaOH is our base. That's the molarity of our base. And then VB, well, that's the volume of base that we used. And so this is our VB. Now again, why am I using these averages? Well, you guys, I saw some of you on our test last week. You did the MA, or you calculated the MA using the VA, the MB, and the VB for trial 1, and then you did it for trial 2, and then you average the two together. And you can do that, but you don't need to because we have the averages here. Let's just go ahead and use the averages that we've already calculated so that we don't have to do a molarity for each trial and then average that. Let's just go ahead and use our averages. So this is our VA, this is our MB, this is our VB, and we're solving for our MA. So let's go ahead and substitute our numbers in, and of course I can't see it. So I'm going to move it over a little bit more so I can see it while we're substituting. So again, our MA is what we're solving for. Our VA, we said, is this right here, the 25.0. Our MB is this 0.750 molar. And our VB is this 25.56 milliliters. Molarity of our base, which is the NaOH. Okay, so now to solve for our MA, we're going to divide both sides by 25.0 milliliters. So 25.0 milliliters cancel out. We have MA over here. Over here, the milliliters cancel out, and we're going to have molarity. So we got to substitute this into our calculator. We're going to do, and I'm going to have to move this back over a little bit so that we can see our answer. So we're going to do 0.750 times 25.5 equals, and then we're going to divide by 25.0. And, wait a minute, guess what I didn't do again, guys? Oh, I make myself so mad. Got to clear it out. So again, 0.750 times 25.56, 25.56 equals, divided by 25.0. And that gives me 0, and again, everything that we're using here, the least number of significant digits is 3, so we're going to use 3 significant digits, so that will be 0.767 molar for our MA. And that's what I wrote here, 0.767 molar for our MA. Okay, going on, we're now looking at number 11. So number 11. If the actual molarity were 0.80, calculate your percent error. Use your average molarity to do this calculation. Okay, so again, our average molarity that we calculated was 0.767 molar. So our molarity that we calculated was 0.767 molar. All right, so we're going to have to use this equation. And again, the actual molarity is 0.80 molar, it tells us here. So you guys, in our equation, that 0.80 is our actual. So that's what you put on that's where you put where it says actual. So do your percent error. Your actual was 0.80. Some of us can mess that up. And then on the bottom, you put the 0.80. And then your experimental, well, that's what we calculated up here. I even have it here for you. Experimental acid molarity. And that was our 0.767. 0.767. Okay? And then you'll multiply that by 100. So going to our calculator, we're going to have, and again, you guys, these little lines right here just mean absolute value. So if you were to get a negative number, just make it positive. So we're going to do 0.80 minus, now wait a minute, let me clear again. 0.80 minus 0.767 equals, and then we're going to divide that by 0.80. And we're going to get this. Now we've got to multiply that times 100. And we get 4.125, but again, we got to look at significant digits. If we look at that 0.80, it has only 2 significant digits. So we're going to round this to just 2 significant digits. So 4.1, the 2 does not change the 1. So we get 4.1, and this is percent. 4.1% error is our final answer. So that's not bad at all. Let's look and see if we calculated that correctly on our answer sheet. So we have, let's look at our data table that we filled in, 25.5, 25.62. Let's just look and see. Okay, 0.7671, except that we rounded it to 3 significant digits, so we actually got 0.767, so that was correct. And then since we use 0.7671 here, we got 4.3%, but just using the 0.767, we get 4.1%. So again, we're basically right there at the correct answer. All right, so let's look at our last problem. And I'm going to go back up here to the top, and I'm going to clear this so we can do our last problem, which is number 12. And we have a redox reaction, and we want to identify the oxidizing agent, the reducing agent, and balance the equation. So I'm going to write this equation on my iPad. Fe plus 2 plus H2O yields Fe plus 3 plus OH minus. All right? So I'm not going to identify the oxidizing and reducing agent yet. What I'm going to do first is I'm going to go ahead and write my half reactions, and then I'll do the oxidizing and reducing agent, because I have to figure out what's being oxidized and what's being reduced before I can do my oxidizing and reducing agent. So again, I'm going to look at the Fe first. The Fe went from Fe plus 2 to Fe plus 3. So actually, before I do that, was that oxidized or reduced? Okay, well, the charge went up. So when the charge went up, that means it lost electrons. When the charge goes up, it has been oxidized. So you may want to go back and review your definition of oxidation and reduction. So the Fe was oxidized. So I was writing it in the wrong place. Okay. And then our H2O became OH minus. So H2O, OH minus. And so then, and what we have to do here, obviously, is we have to look at the charges. So I don't need to exactly do it like that. We have to identify the oxidation numbers of everything. We have the oxidation numbers of the Fe's, but we don't have the oxidation numbers of the H and O yet. So the H here, remember, O is -2, H is +1, because there's 2 of them. So that's a total -2 charge. So we need a total +2 charge here. So that means each H must be +1. So H is +1. And I can't get that to stay there. Okay, then over here, the whole OH is -1. Okay? Well, if the O is -2, as we said, the H must be +1 for us to get hold on just a minute, because it doesn't look like the O and the H changed, and it has something changed somewhere. It had to. Hold on just a minute. Oh, and if people would quit texting me, I would be able to concentrate on this a little bit harder. So let me see here. The OH has a -1 charge. Let me look and see what I put here on it. Let's just look at the answers here. Because I cannot concentrate for all these people texting me, and I really apologize for that, guys. But anyway, here's our problem. It's not H2O. I've written that equation down wrong. It's H2O2. Okay, there's my problem. I knew something wasn't right. Okay, so, okay, anyway, so this changes things a little bit. I knew something wasn't right here. That's the problem. All right, so this is correct, but for this one, if this is H2O2, O is -2, so that gives us a total -4 charge. And so then we need to have a total +4 charge because this is a neutral compound with a charge of 0. So if there's two H's, each H must be +2. So H went from +2 to +1. So its charge went down, which means it was reduced. So, sorry about that. So, our H2O2 became OH minus. And again, we don't even have to write it like that. We can just put H +2 became, and this H2 +2 became H +1. Okay? So this H2 with a +2 charge became H with a +1 charge. All right, so now the first thing we have to do is balance our atoms. So in this top one, there's two H's here, one here, so we have to put a 2H here. Okay, in the bottom one, we have one Fe on both sides, so it's good. All right, next, we have to balance our charges. So again, remember, the only thing you can add are electrons, which are negative. So you're going to have to add negative electrons to the higher charge side to bring it down to the lower charge side. Okay, so here we have 2 + 2, so we have +4. Here we have 2 + 1, so we have +2. So we have a +4 over here, we have a +2 here. So this means we're going to have to add 2 negative electrons to this side to bring that charge down to a +2. Again, I added electrons to my higher charge side. So I have 2 negatives, 4 positives. That gives me +2 over here, and then I have +2 over here. Okay, so then let's look at our bottom one. We have +2 here, +3 here. So we're going to have to add electrons to the higher charge side to bring it down to the lower charge side. So +3, we're going to do +1 electron. And that is going to give us +3 and -1 here gives me +2, and then we have +2 over here. Okay, the last thing we need to do is we need to balance the electron. We need to have the same number of electrons on both sides of both equations. So we have 2 negative electrons here. We have only 1 here, so we have to multiply this entire equation by 2. And when we do that, we end up with 2 Fe + 2 yields 2 Fe + 3 + 2E minus. Now we can check and make sure our charges are still balanced. Now we have +4 here. We have +6 minus 2. We have +4 there, so they're still balanced. Okay, so now we don't need this one anymore because we just got this new one. Now we can cancel out these negative electrons on both sides. And now we can add both sides together. So on both sides, on the left side of the arrow, we have 2 Fe + 2 plus H2 with a +2 charge. On the right side now, we have 2H plus 2 Fe3 plus. Okay, so now we take those coefficients that we have here and we put them up here. So 2 in front of the Fe2 plus. Nothing in front of the H2 + 2, so that's this one. 2 in front of the H plus, so that's this one over here. We need a 2 in front of this that has the H plus in it. And then we need a 2 in front of the Fe3 plus. And this equation should be balanced. Now, you know, if we want to get rid of some of this extraneous stuff, we see we have 2 Fe's on the left, 2 Fe's on the right. We have 2 H's on the left, 2 H's on the right. We have 2 O's on the left, 2 O's on the right. Now let's check our charges. We have +4 here, and we have +4 here, so that's +8. And then we have minus 4 here, which is minus 4. So plus 4 is plus 8. Minus 4 is plus 4. That's what we have here. Over here we have plus 6, and we have, this is negative here, and this is 2, so 2 negatives. So plus 6 minus 2 gives me plus 4. So our charges on both sides are also the same. So now this is our balanced redox reaction. If we, the last thing that we need to do is identify what our oxidizing and reducing agent are. Remember that your oxidizing agent is the thing that was reduced. Since our H2 was reduced to becoming H+, our H2 is the oxidizing agent. Since it was reduced, it is the oxidizing agent. So that means that the H2O2 is the oxidizing agent. Okay? And then the thing that was oxidized is the reducing agent. So our Fe2+ was oxidized to become Fe+3. So Fe+2 is our reducing agent because it was oxidized. So this Fe+2 is our reducing agent. Okay? So let's check and see if what we got is correct with our answers. Okay, we said that our final balanced equation is H2O2 plus 2Fe2 yields 2OH plus 2Fe3+, and that's exactly what we have, guys. And then it doesn't look like I identified the oxidizing and reducing agent here. I forgot to do that on this answer sheet, but again, your oxidizing agent is what was reduced, which was your H2 with a 2+ charge, which was this, that was part of this H2O2, so that's our oxidizing agent. And then what our reducing agent is what was oxidized. 2Fe+2 was oxidized, so that's our reducing agent, and that's what we labeled here. Again, your oxidizing and reducing agent are both on the left side of your equation. Okay. Please let me know if you have any questions. Please fast forward through and ignore a lot of the interruptions that we had and things like that. I'm sorry for that, but my computer is on the same iCloud account as my phone, or I should say iTunes account as my phone, and so any message that I get or phone call comes on my computer, my iPad, and my phone all at the same time, so I apologize for that. You guys, I have really enjoyed having you in class this semester, even though I only got to see you for about 9 weeks. I'm going to miss you guys, your seniors. I'm going to miss you. I don't know if we'll be at graduation, whatever graduation plans they have for you or not. Please come back next year and see me. I wish you good luck in college or whatever you choose to do when you leave Monroe County High School. I wish you nothing but the best of luck. Please stay safe and stay healthy, and come back and see us if you can, because I'm really going to miss you. Please let me know if you have any questions about anything. In addition to completing this final this week, that's the only thing that you have to do besides just any makeup work that you want to do. So please check Infinite Campus. Check Google Classroom and see if there's any assignments that you haven't done. Check Infinite Campus and see if you have zeros. See if you have things that I have, because I will have a note on there that says completed work needs to be turned in. So if it says completed work needs to be turned in, that means you haven't done that assignment, or it means you haven't done that entire assignment. So go back to Google Classroom and look at it and do it. I will grade it. If there's anything on there that you want to try again, you want to redo to make a higher score, email me and let me know, or send me a message on Google Classroom, and I will go back and I will assign it to you again on Google Classroom, or I will reset it or something so that you can submit that assignment again. Again, we'll talk to you guys later. Hopefully, come back and see us, and good luck in whatever you choose to do. Have a great summer, guys. Bye-bye.